morning. William, can you hear me okay?
Yeah, we can hear you.
Great. All right, well, it's 10 o'clock, so let's get started. I hope you all had a nice weekend, and just a couple quick announcements. So as a reminder, our Chapter 3 quiz will be on Monday. So as usual, you'll need to find a 1-hour period to take the Chapter 3 quiz. It'll open right after midnight, and then it'll close at 11:59 p.m. on Monday. This week, William will be having a review of all the derivative stuff that we've been going through on Thursday. So by Thursday, we'll have all of our sections covered from Chapter 3. And so he'll be doing the review that is posted on Moodle under where the Chapter 3 quiz heading is. So if you think that that might be helpful for you, definitely check it out. Other than that, we're just still plugging along in Chapter 3 and learning our derivative techniques. So today we are going to be learning about something called the product rule. And so I just want to remind you that the word product means that we're multiplying two things together. So if we talk about the product of 3 and 4, that would be 12, because the product means we're multiplying two different things together to get some sort of result. Okay, so I'm going to go ahead and switch over to the DocCam. Oops. Okay. And so let's talk for a minute just about the product rule in general. Again, the way that we are going to recognize that we need a product rule is that we have two functions multiplied together. So f of x times g of x. And notice that I can draw a line right in between the two functions that I'm multiplying together to separate them into two functions. Each one needs to contain our variable. And this is important because we're going to need to start recognizing when we need to use a chain rule versus a product rule versus on Thursday, we'll learn the quotient rule. So we're still looking at forms to figure out which rules we're applying. So the product rule comes from applying the definition of derivative using limits. I'm not going to do out the definition of the derivative with the limits just because there's sort of some tricky pieces that end up in here and I don't want to confuse you, but do know that this is how this formula comes to be, is by applying this definition. And so the formula that we get from this is that if you have one function times another one and you want to take the derivative, the product rule says it's going to be the derivative of the first function times the original second function plus the original first function times the derivative of the second function. So what does that mean? What does that look like in practice? We're going to go through one so you can see, how it works out, how we apply this, what the formula looks like. So we're going to do this with the example x squared e to the x. Okay. So the first rule of any function is we are looking at the function to determine what we need to use in terms of rules to take derivatives, right? Sometimes we can just take a derivative. If we just had x squared, we wouldn't need any special rules. We would use the power rule. But here we have x squared times e to the x. So I notice that times, and I also notice that I can separate these two functions, right, directly down the middle, right? So there's one on the left and there's one on the right. So this is not a chain rule because chain rules you cannot divide up down the middle. So here I have a product rule. And so for the product rule, I have two distinct functions. They each have my variable of x. I'm going to call one of them f and one of them g. Technically, it doesn't matter which one is f and which one is g, but the convention is that you pick the first function you see in order to be your f and the second function to be your g. Okay, so here, my f is x squared and my g is e to the x. Okay, now by splitting these up into two different functions, into their sort of original parts, the goal here is hopefully when I take the derivative that I know how to take the derivative of each of these pieces. And I want you to notice that whenever I take derivatives underneath the original function. For me, this creates a map that I'm going from original to first derivative. And if I were to do a second derivative, I would put it underneath. And the reason I do that is it helps me For later in this course or in 128, when you have to go back in the other direction, then I go up and it helps me keep organized. You don't have to write things the same order that I do, but I find it somewhat helpful. So I want to take the derivative of x squared, and that's a power rule, and that's going to give me 2x. I also need to take the derivative of e to the x. The derivative of e to the x is e to the x. Now, the product rule says I have to multiply f prime times g. I'm going to cross multiply this way. And to that, I need to add f times g prime. So the product I get when I multiply this way. Okay. So that means here, when I want to find my derivative of this entire function, I'm going to do 2x times e to the x plus, and I'm going to multiply this way, x squared times e to the x. Okay, and the convention when you're multiplying things together, so if you look at this term here, is that you write the constant in front and then your terms in order of increasing difficulty. So you're technically you don't have to do this, right? Because like e to the x times 2x is the same thing as 2x times e to the x. But just for recognition purposes, like on a mini quiz, you want to make sure that you can recognize that your answer is the same as another rewritten answer. We're going to have the constant first, then any polynomial terms, so x, x squareds, x cubes, then exponentials and logarithms. Okay, so this is what the answer would look like if it was on a mini quiz. We could certainly factor this. We are not going to get too much into factoring right now. We're going to do a whole lot of factoring in chapter 4, but you should feel comfortable sort of pulling out something like an e to the x, for example. So I guess we'll just do this real quick. So if we were to pull out an e to the x, right, you're left with a 2x plus x squared. Okay, so you should be able to recognize that these are the same thing. So if this is what the answer looked like on the mini quiz, that you would know it was the same. Okay, so that's how the product rule works. We divide it up into two functions. The first one we call f, the second one we call g. We find each of their respective derivatives, and then we apply the rule that says f prime times g plus f times g prime, and we put it all together to get the derivative of our function. So let's go ahead and I'm going to have you try this next one. So the derivative of the natural log of x times e to the 6x. So again, I can divide it right in half. So I know I'm using a product rule here. So you're going to pick one of them to be your f and one of them to be your g. And just as a reminder, when you have a 6 up in the power, you have to remember to be careful when you're taking the derivative of that. Okay, so try this out. I'm going to give you 2 minutes. See if you can set up the same sort of pattern here for this particular problem, and then put it all back together to get your final derivative. And then we'll go through it together in about 2 minutes. All right, take about 30 more seconds. All right. So again, I have two functions. They both have my variable in it. I'm going to pick one to be f and one to be g. So the first function I see is the natural log of x. So that's my f. And my second function is e to the 6x. Now I want to find the derivative of each of these separate pieces. So the derivative of the natural log of x is 1 over x. And the derivative of e to the 6x is 6e to the 6x. So remember, if you have a constant up here, it comes out. The power does not change. Otherwise, that's what the derivative looks like. So now, putting this together, I'm going to do f prime times g. So I have 1 over x times e to the 6x plus g prime f. So 6e to the 6x times ln x. Okay, so there's not a whole lot of simplification I would do here. You could factor out an e, so let's see what that looks like. So e to the 6x, if we were to factor that out, from the first term, we'd be left with a 1 over x. And from the second term, we'd have a 6 times ln x. Okay, so these are the two common ways that you would see the answer written here for this particular derivative. Okay, so I think the trickiest part here is remembering this particular derivative here. So if you didn't remember, that was 6e to the 6x, put like a star next to it to remind yourself. Okay, so that's how the product rule works. And now we can use it to do all the things that, we normally do. So we're going to try a couple applications here. As you probably guessed, we're going to look for the equation of the tangent line, right? So we've done this several times now. We need a point, we need a slope. So the difference here is that our derivative happens to be two functions multiplied together. So we'll have to use a product rule. Example 4, you're going to be looking for both a first and second derivative for our function. I do recommend that you simplify the first derivative if you can before you find the second derivative. So these two problems, these are just typical problems we've been trying throughout all the types that we've learned. So equation of the tangent line and first and second derivatives. So I'm going to give you about 4 minutes to try these out. You can do them in either order, whichever one you feel like tackling first. But hopefully it'll help you practice the product rule as we go along. So take about 4 minutes and then we'll go through it together. All right, take about 30 more seconds. All right. So for the first one, equation of the tangent line, hopefully you're starting to be pretty comfortable with this concept now. We need a point and a slope. So let's start by finding our point. We're going to plug 0 in here to get our y value. So cosine of 0 is 1, right? So cosine starts at 1, and e to the 0 is also 1. So that gives me a y value of 1. So my point here is 0, 1. To get my slope, I need to find the first derivative of my function. Well, I notice here that I have two terms that can be completely separated by a vertical line. So I know I need to do a product rule. So I'm going to sketch that out up here so that I can plug in the solution after. So the first function I see is cosine. The second one is e to the x. I find each of their respective derivatives. The derivative of cosine is negative sine. The derivative of e to the x is e to the x. So now I'm going to cross multiply. So f prime times g gives me negative sine x times e to the x plus g prime times f. So I have e to the x cos x. So my derivative looks something like this, and I want to know what that value is at 0. So I plug in a 0 everywhere I see an x. So here, sine of 0 is 0. So this whole first term gets canceled out to 0. And then here I have e to the 0, which is 1, times cosine of 0, which is 1. So I have 0 plus 1, which gives me a slope of 1. So now I have y equals 1x plus b. So the slope is 1. We don't usually write the 1, but just for this step, I'm going to write it. We could just write x and the slope would be 1. So now we want to use our point here. When x is 0, y is 1. So I have 1 times 0 plus b. That tells me that b equals 1. So my final equation of the line is y equals x plus 1. So again, the equation of the tangent line, this process is always the same. What's changing is the derivative because we're doing different types of functions here, but the process is the same. Find a point, find the derivative, find the slope, put it all together, and you get the equation of your tangent line. Okay. Now for our second one here, we have a function ln x times x to the 5th, and we're looking for both the first and second derivative of this function. So I think the first derivative is pretty similar to the ones we've been doing, so that one shouldn't be too tricky. But the second derivative does have some, things we have to be careful about. So I'm just gonna draw some space up here. I didn't leave myself enough space, so I'm gonna work here for the first part. So again, I notice I can divide it into two functions. The first one I'm going to call f. The second one I'm going to call g. So now my next step is to find each of their respective derivatives. So the derivative of the natural log is 1 over x. The derivative of x to the 5th is 5x to the 4th. So now my first derivative here, f prime times g, so I have 1 over x times x to the 5th, plus g prime times f, so 5x to the 4th times the natural log of x. And so I mentioned before that it does help to simplify this first derivative before taking the second derivative. So if I look at this, the second term can't be simplified, but the first term, I have 1 over x times x to the 5th. So this x that's here can cancel one of the x's here. So I can write this as x to the 4th plus 5x to the 4th times ln x. Okay, so that's what my first derivative looks like. If I was only looking for a first derivative, I could stop here. But of course, I'm also looking for a second derivative. And so what I'm going to do is I'm going to go term by term to figure out what my second derivative is going to look like. Okay, so if I take the derivative of x to the 4th, I get 4x cubed. But then if I look at the next term, 5x to the 4th ln x, I can't just take the derivative using my regular rules. I need to use a product rule because I have two things multiplied together. So say, okay, well, my first function is my f, so 5x to the 4th. The second function is my g, that's the ln x. The derivative of 5x to the 4th is 20x cubed. Derivative of ln x is 1 over x, right? So now I have to do f prime times g. So remember, this was a plus in between, so I have plus f prime times g, so 20x cubed times ln x plus g prime times f, so 1 over x times 5x to the 4th. So now that's the derivative of the second term. So I want to see if I can do any simplifications. So I notice that that last term I can simplify. So I have 4x cubed plus 20x cubed ln x plus, now again, I have 1 over x times 5x to the 4th. This x will cancel one of these x's, and I get 5x cubed. And so now what I notice is that I have a 4x cubed and I have a 5x cubed. So I can combine those into 9x cubed plus 20x cubed times ln x. Now I could factor out an x cubed term if I wanted to. I don't need to. I don't have any reason that I'd want to do that right now, but I could. Okay, so this is sort of the final simplified version of our second derivative. So the key things that I needed to notice is that when I had my first derivative, I could just take the derivative of the first term, but I needed a product rule to take the derivative of the second term. So that's what we have to start noticing within our problems, is what this looks like to tell us that, hey, we need a product rule. Okay, so now we're going to try another problem. That's a word problem. And there's sort of a lot of parts here. And what I want to say about this problem is that even if you don't know what the situation is in this problem, we have a function to work with, and we can use what we know about functions and derivatives to answer the questions. So here's the situation. The wave function for our harmonic oscillator, which is like a vibrating chemical bond or vibrating other types of atoms, can be written as psi equals a times e to the negative x squared. That's really small, so I'm just going to write that again over here. That's our function that we're looking at here. And it says where x is the distance from the equilibrium position. So if you have an atom that's vibrating, it has a starting position, and we're talking about how far away it is from that starting position. A is a constant. Part of the process of working out kinetic energy, so thinking about how much kinetic energy is being used or not used for moving this atom that's oscillating, deals with derivatives of this function. So this gets used a lot in both higher level mathematics, but also some physics. So here, this is the Greek letter psi, right? A we said is a constant, and then we have e to the negative x squared, where x is the distance from the equilibrium point. So here are the three questions. So part A, Identify the independent and dependent variable for this equation. So this goes back to chapter 1, right? When we talked about independent and dependent variables, how do we figure out what they are? So we want to do that here so we know what we're working with. Part B is to find the first derivative of this function. So it helps to know what the independent variable is. So you can take the first derivative. I want you to notice or hopefully figure out that to take the first derivative, we actually have to do a chain rule, not a product rule for the first derivative. And then C, find the second derivative. And it's when we find the second derivative that we then need to use a product rule. Okay, so I want you to take about 3 minutes, try out this problem, see which parts you can figure out, and then we will go through it together. All right, take about 30 more seconds. All right. So when we're thinking about what is our independent and dependent variable, we need to use both context clues, but also information from the setup here. The dependent variable here is psi. So put D for dependent. And we know this because the oscillation depends on what's happening on the right. Also, typically the dependent variable appears on the left-hand side of the equation. Now, the independent variable is going to be our x. So I'm going to put an I for independent variable. We know that A is a constant. We know that E is a constant. E is always a constant. And we know that X represents the distance, which is the thing that we can control. So that's how we identify our dependent and independent variables. Now, when we talk about the first derivative of this function, psi prime, right? We just need to remember what is our independent variable here, because here we also have an A. And since A is a constant, we need to use the constant multiple rule, which means that our A is going to multiply the derivative of e to the negative x squared. So now we're in a situation where we have a chain rule. So we could either do some of our reasoning through that we talked about with one method or a z substitution. I'm not going to do a z substitution just because of space, but if you did a z substitution, your z would be negative x squared. So here, when I take the derivative of an exponential, I get the same thing back, e to the negative x squared. And for ease, I multiply this by the derivative of the power. So the derivative of negative x squared is negative 2x. Now, as I mentioned before, we typically write constants first and then polynomial terms. So if this was on a mini quiz, the way that you would see the answer is probably something like negative 2ax e to the negative x squared. And it's totally fine if you've written it like this, just to check each piece, like, is there an A? Yes, there's an A. Is there an e to the negative x squared? Yes, there's an e to the negative x squared. Is there a negative 2? Yes. Is there an x? Yes. Okay, they are the same, right? But this is sort of the way we rewrite things. So that's our first derivative here. We also want to find the second derivative for our function. And so what I want you to notice is that, again, we have x's in two places, okay? And since we have x's in two places, the question is, can we split up these functions by just drawing a line? Yes, we can, okay? So I am going to do my product rule on my sort of rewritten version, but you could certainly have done a product rule, with a e to the negative x squared and negative 2x. There's a lot of different ways you can do it. It doesn't actually really matter where the constants end up. What matters is where the x functions end up. So let's do this over here. My f is negative 2ax. My g is e to the negative x squared. I want to find each of their respective derivatives. The derivative of negative 2ax is negative 2a. So this is a linear term. And so the derivative is just the constant here. For e to the negative x squared, that's the one we just talked about. So we have e to the negative x squared times the derivative of the power, which is negative 2x. So now putting all these things back together, we have f prime times g. So negative 2a times e to the negative x squared plus g prime times f. So e to the negative x squared times negative 2x times f, which is negative 2ax. Okay, so now I have all my pieces. I want to see if I can simplify anything here. Oops. Psi double prime. So I look at the first term. It doesn't look like there's anything that can really be simplified. The constants are already at the front, so I'm going to leave that as is. Now, when I look at the second term, I think about what the constants are. So I have a negative 2 here and a negative 2a here. So the negatives are going to cancel, and I'm going to have 4a. So those are my constants. Then I look at my x terms. I have an x here and I have an x here. So when I multiply my two x's together, I get x squared is my next term. And then I have my e term. So e to the negative x squared. So my second derivative simplifies to look like this. Now we can factor this all sorts of ways. We could pull out the e term. We could pull out the a. We could pull out a 2. But we're not going to factor it because we don't have a reason to factor it right now. Like I said, in chapter 4, we're going to spend a lot of time factoring because we're going to be finding out when each of these things equals 0 or 1 or things like that. But for now, we don't need to factor anything here. So what I want to point out again is that for our first derivative, we didn't have to use a product rule. We had to use a chain rule. But the chain rule resulted in the second term that created the need for a product rule to go to the second derivative. So even if you don't use a product rule to get the first derivative, doesn't mean that you won't need a product rule for the second derivative, okay? So as you can imagine, there are a lot of times where the product rule is used, but has things like the chain rule involved within it. So we're going to look at one now that's a product rule, where the terms that we're using within the product rule also are chain rules. So here we have the function sine of x cubed times the natural log of x squared minus x plus 1. First, I can divide this straight in half with a vertical line. So I am using a product rule here, where my functions are sine of x all cubed and the natural log of x squared minus x minus 1. Within that, once I set them up as my f and my g, I do have to use a chain rule to find their derivative. So it's a little more complicated than the ones we've been looking at before, but hopefully you remember what we were doing on the chain rule. So I'm going to have you give it a try, see what happens. Ooh, that's sliding down. So I'm going to give you about 2-3 minutes. Try this one up, set it up as normal, see what you can remember about the chain rule, see if you can put it all back together, and then we'll go through it together. Okay, so try it out. All right, take about 30 more seconds. All right, so the first thing I want to point out is just sort of an algebraic not correction, that's not the right word, just, well, let me just show you. So I just want to point out that sine cubed of x, if the cubed is here, that's the same thing as sine of x cubed. So if you see something like this on Wiley or on a quiz, this means the same thing as if you had sine of x all raised to the third power. For some reason, some algebra classes don't teach that. So I just want to make sure you know it's the same thing, just in case you see it written that way. So now I want to separate my two functions. So the first one, I have sine x cubed, and my second function, I have the natural log of x squared minus x plus 1. Okay, so obviously when I take these derivatives, they're going to be a little more complicated and a little bit longer than the ones we were working on before, but hopefully you remember from last week how we do these particular chain rules. So here, this is in the power rule form. I see the variables down here in the base, and then everything is raised to a power. So the chain rule says that the 3 is going to come down, everything inside stays the same, and I subtract 1 from the power. So that's the power part of the power rule. But I have to remember to multiply this by the derivative of the inside. So the inside is what's not part of the power. So it's that sine x. The derivative of sine is cosine. So my f prime looks like this. And then my g prime, I have a natural log type. So the natural log type says I can do 1 over whatever is in the argument. So x squared minus x plus 1. But I have to multiply that by the derivative of the inside, which gets multiplied into the numerator. So the derivative of x squared is 2x. The derivative of minus x is minus 1. And the derivative of 1 is 0. So now I have all my pieces, so I can put them all together to get my final derivative here. Need lots of space. So I'm going to do f prime times g. So I have 3 sine x squared times cosine x. That's my f prime times g. So times ln x squared minus x plus 1 plus, now I'm going to do f times g prime. So I have sine of x cubed times 2x minus 1 over x squared minus x plus 1. So this is not a super easy derivative, right? There's a lot of pieces and a lot of things that are all put together in this type of problem. But as we learn new rules, we have to also remember how to apply the other rules we've learned within those rules. And so again, being organized and being careful in writing out all your steps is really important to getting to the final answer when they're big and long like this. I will tell you one of the main things that students would get wrong in this particular problem, which you may or may not be surprised about, is this term right here. So for some reason, when the x is by itself and students have to take the derivative, sometimes they forget that the derivative of x is just 1. And so this term disappears, right? So that tends to be something that gets left off, which makes the whole entire problem wrong. So even though that's sort of a minor thing, it really, every single step impacts the whole problem. So just be really careful as you go piece by piece and try to write everything out so that if you do get something wrong, you can review each step that's in between to see if you can figure out where you made a mistake. Okay. So the next problem is going to give us some insight into what we'll be doing on Thursday. Oh, my line disappeared. There should be a line here. I don't know why that didn't print. So we are thinking about the function e to the x divided by x to the 5th. And I want us to think about how we might be able to use the product rule on this function. And hopefully you're thinking, well, we don't have one thing multiplied by another, which is the key structure that we need to use a product rule. So the first step is thinking about how can we rewrite this function so that we have two things multiplied together. And my hint for that is that we don't want to have a function in the denominator. So think about how to get that term out of the denominator. And once you do that, you should be in a good setup to do a product rule. Okay, so I want you to try this out. I'm going to give you about 2-ish minutes. After a minute, I'll do the rewrite. So if you don't get that part, you can at least build from there. But try it out and then we'll go through it together. All right, take about 30 more seconds. Okay, so hopefully you're able to figure out that the way that we're going to rewrite this is by bringing this x to the 5th term up by making the power negative. So that's a thing that we've done before when we were talking about derivatives and some algebra stuff. So hopefully that's what came to mind when I said you needed to rewrite this. When we bring it up, we again notice that we have two things multiplied together. We can completely separate them. And so we are able to think that we can use the product rule. So here, my first function is e to the x. And my second function is x to the negative 5th. Right? So now we want to take each of their respective derivatives. The derivative of e to the x is e to the x. And the derivative of x to the negative fifth is negative 5x to the negative 6. So remember, when you have negative exponents, they get more negative when you take the derivative. So then plugging into the product rule, I'm going to do f prime times g. So I have e to the x times x to the negative fifth plus g prime times f. So negative 5x to the negative sixth times e to the x. Okay. So how might we rewrite this? So typically we're gonna change any negative powers back to being positive. So we might rewrite this first term as e to the x over x to the fifth. That's another way you might see this term. And then here we had plus a negative. So we're gonna write that as minus. And then here, the 5 and the e to the x are gonna stay up in the numerator because those don't have negative powers, but the x to the sixth term, we can put down here in the denominator like this. So we can simplify the second term to look like this. So these two things are the same, okay? And so again, you don't need to rewrite it, but you do need to recognize that it can be rewritten like this, because if this is on a mini quiz, you want to make sure if you see this, but you've written this, that you know it's the same thing, okay? So that's the derivative here. So as I mentioned, this is sort of a starting off point. We're actually going to do this problem again on Thursday when we do what's called the quotient rule, when you have one function over another one. But it's important to know that you can rewrite these types of functions to be product rules by bringing whatever is in the denominator up using these types of algebra rules. So that's it for today for the product rule. We're going to stop here. I'm not going to make us do any more work because I know everybody needs a little bit of a break. I do recommend doing the product rule homework before you do Wednesday's mini quiz. So just look for the problems that use the product rule, do those homework problems, try the mini quiz, and then we'll do the quotient rule on Thursday. Okay, hope you have a great rest of your day.